Lab lecture, let's take a look at how you can do some basic data cleaning in Stata. At the end of this, I'll loop back around to how to use the ICPSR, which is a useful repository of data sets pertaining to the social sciences. I'll talk about some other methods for selecting data sets, but just searching, doing simple searches on that website is a pretty foolproof way to go. So let's first start by accessing the lab exercises that I put into the folder for this week. So we'll manually access my GitHub by going to tinyurl.com/SOC361fa24. I would recommend bookmarking this website. You can also navigate directly to my GitHub here. For those who haven't used GitHub before, hopefully you remember from last week, but for those for whom that was their first experience with GitHub, GitHub is the mainstream way that people share code and data in the programming community broadly. So among sociologists, political scientists, even people who have PhDs in social work or even medical research, if people do quantitative research, this is the way they post things. So I don't mean to use a website that seems needlessly obscure or anything like that. What I hope to do instead is introduce you to how people currently basically do project management, or what's sometimes called version control, which is a more specific term. We talked about that a little bit when we looked at my syllabus, and I mentioned some general project management guidelines, but we'll go over that in more detail later. For now, I just want to focus on one aspect of that process, which is using Stata to process your data in a way that obviates the need to do so using Excel and leads to more reproducible results. In fact, you could say in the way that it's really the only way that you might get reproducible results. In general, manually managing your data with something like Excel, which is admittedly how I proceeded for the first few years of grad school, using Stata as needed, but I was sort of Excel reliant. Generally speaking, this produces a workflow that is almost never reproducible, which is bad. Okay, so let's navigate to week 2. And we'll also talk about the where standard errors come from at the very end of this lecture, but we're mostly not going to focus on that. By the way, you can ignore this DS store file. This is just something that is part of the kind of back end of GitHub, and same with this folder here. Essentially, these folders that just have 2 dots, or using 2 dots in a command like change directory, generally just pushes you to the folder that you started from if you're in a subfolder. So here we're in week 2. You can see if I click on the double dots, I just get pushed back to SOC361fa24 generally. You can ignore those 2. It's just kind of a convenience. So what we're going to do is open up the Lab 2 exercises that I wrote for us, and we're going to download these, and I strongly suggest that you go ahead and first of all open these in Adobe Reader, and second of all, if we go find these, right, it's a good idea to go ahead and actually move these to the folder that you use for this course. You can see that my downloads folder is a little bit messy right now. One of my hobbies that some of you might know about is that I'm super into lifting and cooking sort of traditional meat products. So you can see in my downloads folder, I have a lot of sort of random things about bone marrow custard and this sort of thing. Not ideal data management, but the main thing is that when I get files like this that I want to make sure I know the location of, what I do is I move this manually to one of my favorites, and I swap out my favorites fairly often, so you should do this dynamically. Make sure that this sidebar, whether you're on Windows or Mac, is up to date with what you're doing recently. So here I'm teaching SOC361fa24 currently, so I moved that to my favorites, whereas it previously wasn't, and I kind of swapped things out. So the oldest favorite I have is SOC360 Spring 23, but I don't have SOC365 Spring 22, for instance, up here, because that information is essentially kind of superseded, or I don't access it as often. So just a data management tip. Let's move this to the correct folder, and then we'll need to do a little bit more moving as well. You can see here, I would put this, your folder is going to look a little bit different than mine will, but what I would recommend doing is moving this into just the relevant week. So here, I'm going to move it into this week. Some of you may not have a subfolder structure like this. That's okay. you should just have some means of managing your data that's coherent and clear. Okay, so I'm going to now, although it seems a little silly, it's actually a very good idea to go and access it from the folder you actually moved it to. And you can see that I actually have 2 copies of this document because I put the document originally in this folder. Some people asked me questions about that on the first day of lab, actually. This is a common snafu when you're doing programming, which is that if you try to manipulate files, open files in Stata, move files around, etc., you don't want multiple copies of the same file circulating on your computer. So here you can see Windows, or a Mac in this case, has automatically appended the number 1 to this PDF because I have 2 copies of it in here. If you are sure that they're the same file, and generally the computer is smart enough to only add this number if they're the same file, or they have the exact same name, at least, you should generally inspect the documents. So this kind of looks like something I already have in here. Okay, they look almost identical. So what I'm going to do is actually just delete this one that's got the 1 because we don't really need 2 copies and it can actually be confusing. For instance, if I open that copy, one problem with that is that then I'm making modifications to a document that actually has a name that suggests it's backup or secondary. And people very often get confused about these things. So just a word to the wise. By the way, you should also frequently empty your trash on your computer after making sure that you don't have any files in there that you need to review. So that's a good tip as well. So now let's open this in Adobe Reader, which is a good place to open PDFs. So we'll just drag like that. And let's dive in. So the purpose of these exercises is to get you familiar with the process of importing and transforming data. So we're going to start with importing data. Here's what I suggest that you try to do on your own. You can pause the video after I describe this and then try it out. I would suggest that you try to write a set of commands that import the 3 data sets from my GitHub for week 2. So if we tab back to GitHub, by the way, if you're on a Mac, and I'm sure there's an analogous way to do it on Windows, you can hold down Command and then click Tab while holding down Command to navigate between programs. So here we can navigate to Firefox by just holding down Command and tabulating, and you can see it can actually navigate through these windows. Learn these hotkeys, they'll save you a lot of time. Okay, so we have this PDF already open in Adobe. We're going to close it and then just look at GitHub. Here, I'll just click on the main directory for this week. And I see that what I'm going to want to open are the DTA files. So the CPS extract, the GSS 2018 full data set, and this is the Detroit area study full data set. The CPS is massive, so I only extracted some of the information. GitHub doesn't let you upload documents in excess of 100 megabytes, which is, for those of you who don't know, a fairly large file. Most, social scientific data sets are 5 to 10, something like that. 100 megabytes is more in the order of a long record ripped to very high quality. Okay, so you can't put things like that on GitHub because flat data files, essentially the data files we actually use, are usually much smaller. Okay, so we want to download these 3 things. I would again suggest downloading them really one of 2 different ways, perhaps. By the way, you can just click on the file. No need to click on View Raw. You can just come here to the download button. And I would recommend putting these in either, by the way, I don't like to see these folders this way. So what you can do is actually choose to view these in a different way. Show items as icons. You can show them as a list. I prefer that personally. So that's just a little computer tip. So I would recommend putting these either in the folder for this week or just an omnibus data folder. It's really up to you. Here, I think I'm going to use the data folder structure, but you can do it either way. And you can see I actually already have 2 of these files in here, so I'm not going to re-download them. So I reposted some files that are already in, presumably, many of your local machines. So don't re-download them. Again, there's no reason to do that, and it just creates a proliferation of confusion. So here, I've already got the GSS 2018, I've already got the CPS 2019 in this specific directory, not just somewhere on my computer. I actually have many copies of this on my computer, which is not best practice, but sometimes that's okay if you want copies for specific reasons. But here, I'm definitely not going to repopulate the directory with that same data set. I do realize that I don't have the Detroit area study, so I'm going to go get that one course, that's already on my computer, but it's in the public version of the folder that I'm posting, and that is not the folder I'm going to work out of. You will only have one version of the folder because you're not posting to my GitHub. Okay, so we're going to come here to data and punch this into the data folder, so DAS 1967. And we also want to get the codebook as well. Inspecting codebooks is extremely important, so we're going to take a look at that. And here you can see it just auto downloads. That's a somewhat annoying property of Adobe, but I can go find that file on my computer by just clicking here on the magnifying glass. It's in my downloads folder, so I'm just going to drag and drop. Yes, there's the faster way to do this with the terminal, which is this program here, which is basically like Stata, but for your operating system rather than for a specific piece of statistical software, but I don't want to get into using terminal. TLDR, if you like this stuff and you want to be a quantitative researcher, you got to know how to use the terminal. So we're going to move this. It's a little bit, hard to say for certain where this should go. I'm going to plug it into the data folder, but you could make a case for putting it elsewhere as well. You just need to think about why you're doing what you're doing and not do things sort of at random. Okay, so we've gotten the data sets. Great. Now what we want to do is go back to my set of exercises here. And here I suggested that you download these manually rather than directly call them from my GitHub. That's all that means is we just went and physically clicked the download button rather than put that into the Stata set of commands. Now, at a more advanced level, you'll want to be able to download them from Stata, but I didn't think that was worth the effort. And in many cases, like the ICPSR, you need to log in to the website in order to download things. And so for that reason, you can't actually directly call data from scripts without a lot of extra work because you need to supply your login credentials. So even though it's ideal workflow, which is something that when you've done this long enough, you'll really come to appreciate it as an aesthetic thing. Ideal workflow is you should be able to pull the data from a public repo, do the analysis, then push your analysis to your own repo, all from a script. But many times that's not possible because a lot of social scientific data sets are old and managed on antiquated systems, such as the PSID or the NLSY, etc., even to some extent the ACS. The GSS is kind of unique in that you can actually just directly download it very easily from the NORC or National Opinion Research Center website, but most social scientific data sets, you can't do that. So doing the entire analysis from a script requires a little bit of finagling. Okay, probably enough said on that. Now what I'd like for you to do is to basically pull these pieces of data into Stata. And I want you to do it successively. So I think I said this like 10 minutes ago now, but now is the point where you may want to stop the video for real and try to do this without watching because I'm about to show you how to do it. But I want you to essentially look at my lab syllabus, hopefully you've downloaded that, and take this pseudocode, right? Pseudocode means that these are not actually things that you could put into Stata, but they express a kind of general idea of how you would tell a computer to do this. Pseudocode, by the way, is very widespread. Lots of books on statistical analysis only provide pseudocode. It's program independent. So what I want you to do is try to convert this into Stata code. That's your task. Pause the video here if you want to try it on your own. I'm going to show you how. So let's dive in. So what you could do is just pull up my syllabus and get what I told you was the way to do this always. It's at the very end of the syllabus. This is called do file etiquette here, this subsection 532. And basically what this does is provide you a copy and pasteable bit of code that you should pretty much always put at the start of your do files because they just execute certain common tasks that you'll more or less always need to do, at least when you're trying to do something that's reproducible. Okay, so how do we open a new do file? We could do it in a couple of different ways. For example, file, new, do file. I prefer, though, to do it from the command line. So do edit. The command line, by the way, I should really say the command window. The command line conventionally refers to the terminal or the shell or whatever different people call it. Essentially, again, the way you issue commands directly to your computer. Here, it's a similar concept. The command window here only applies to Stata, but it's the same sort of idea in that if you come to the terminal here, like for instance, if I just say something like change directory to the desktop, and then I make a new directory called test fun, something like that, and then now I come here and I check out the desktop and I see the folder or directory called test fun. I directly interacted with the computer in an interactive way. You can do that in Stata too. That's what using the command window does, but it's typically more efficient, well, because you want to save your work. Really the only way to save your work is to actually pull up a do file and then put things into this script. And similarly, you really shouldn't typically work from the terminal except to do basic stuff. You would want to open a file, say an atom, and then write down your command. So in every software system, except for Excel more or less, although you can do this in Excel, there's a distinction between interactive mode where you're directly issuing commands to the computer in this kind of dynamic setting here. This, by the way, is just running Jupyter Notebook, so don't worry about it. And then a script, which is something where you can run multiple commands all at once. So one common Stata gotcha is people try to do things like run multiple commands from the command window here when what they really want to do is execute multiple commands as a script or a do file. Or as Rachel Gordon calls it, a batch program, which I like her book quite a lot. I don't like that terminology. It just adds more jargon that no one really uses. So batch program, we're going to say do file or script. And script, by the way, is the name for do files in R and Python in most programming languages besides Stata. Okay, so now we can copy paste my header here. So the first command that we're going to issue is capture log close. This is a bit of a specialty command, so I don't want you to worry too much if you don't fully understand it. Essentially, Stata has a notion of log files, which are files that record what you did when you executed a do file or script, but they aren't themselves actual do files. They're just text files that show the results. This is often useful because it lets other people see your results and see what you did without needing to have Stata available. So log close basically starts a session by closing any existing logs, since that creates a conflict. Capture is a rarely used prefix that is sometimes useful, although I only found it useful after many years of doing this. So probably you won't use this often, but what it tells Stata to do is not stop dead in its tracks if it encounters an error. Why would it encounter an error in closing a log? Well, there may not be a log that's open. So that's a bit of a specialty thing. Now here, this is a little bit more directly useful. We've got the command log using, and this is going to basically provide a text file. That's what this option here means. Options, by the way, are things that come after the comma in a command, and the things that come before the comma are basically the central command. And it's also going to save over any existing copies, which you do with replace. So I generally say here that your file name should be the same as the do file name. And we haven't actually named this do file. So since we've already made some progress here that we like, let's save this. Generally, I insist that you save do files in the following manner. You write year 2024, month 09, day 16, lab 2. And generally speaking, I think you could put your name wherever you want, but let's actually put it right here. So I'm going to write Burr, and then I'm going to write SOC361 Fall 24, Lab 2. Why should you make your files this way, which is sometimes called the year, month, day format? The main reason is that if you don't immediately have a sort by date modified or date added option, which you sometimes don't, or you need to pull it up because not all versions of Finder, like not all instances of Finder have these things. It's kind of complicated to get this to always show up in Finder. What that means is that if you then just sort by the name of the file, you can immediately sort your files in the order of the date. Also, dating them basically helps you immediately execute a kind of version control where if you later make a second copy of this, you can just give it a later date and you immediately know that the later date is the updated copy rather than having to do things like write second draft, third draft, etc. which people often do in confusing and inconsistent ways. So you should write it like this. You should always put your name in things that you might submit to other people. So since you might submit this to me or someone else, you should put your name. And you should always kind of tag it with whatever class you did it for or purpose, and then just essentially the name of the file, lab 2. So I insist that you do this because it is by far the best data management practice. Okay, now let's copy this name because we're going to use it for the log file name as well. And here, we want to make sure, by the way, before we go any further, that this log file, which we'll put here, actually let me mention 2 things. First of all, you see these $signs in my notes. Notice that these $signs that I put here tell you that this is a place where you should put your own information in. So here, I'm going to put quotation marks here and here, but I'm going to otherwise strip out the $signs because they actually do things in Stata that you don't want them to do, but people often use $signs as what are called metasyntactic characters that essentially signal to the user that this is where you should change your code from the provided version to change it to stuff on your desktop. And by the way, let's actually move this command here down to here. This is a little bit, I kind of wrote this a little bit out of order. It doesn't actually matter that much, but let's do it like this. So we're going to write change directory now. Now this part, well, let's actually fix the date here first. So 2024-09-16, author, we're just going to put my name, and purpose, I'm going to say learn to clean data in Stata. And now we want to change the directory. So that's a fancy computer term for we want to tell Stata that the folder that we're going to assume as a default is the folder that we want to pull, that where our stuff is stored for this project. So here, I'm going to get a path to my folder. And in this case, you might notice that I personally chose to save my data in this data folder here, yet I may also want to put this file specifically in the week 2 folder as well. So we might have to navigate between folders a little bit. You'll see that it's not a big deal at all, but you want to think carefully about that when you're, you just want to make sure you know what you're doing. So here, if I think about it, I probably want to do something like this. I probably want to change my folder to this general SOC361 Fall24 folder, and then I'll just add a little bit of information to say where the log should go and a little bit of information to say where we should pull data from. So let's navigate to this folder. And here I'm going to write a path to this folder. I'm going to write tilde/desktop /code /SOC361 Fall24. And I'm going to run this now just to make sure that I can actually get here. To run pieces of code in Stata from a do file, you just highlight them. Here, I can highlight from this line to the top of the do file by holding down Command Shift and then clicking the up arrow on my keyboard. So I do this. Now I can run this portion of the do file by holding down Command Shift and D. And here you can see that I'm able to actually get the fact that I'm in this folder from Stata. I can also ask that in a couple of different ways. First, I could just observe down here. This always has my current directory, but I can also write pwd here, print working directory, in the command window because I may not actually want that in the saved file. I might just want to check it really quickly. So that's a good reason to use the command window. And you can see that, okay, I've got the right folder here. Let me note a couple of other things briefly too. So first of all, I did this in quotation marks. Generally speaking, you should always put folders in quotation marks in Stata. You don't technically need to if your folders don't have spaces, but 2 notes on that. 1, it never hurts. 2, I know most of you, unfortunately, totally understandably, because it sounds pedantic and silly at first, but most of you did not actually remove spaces from your folder names when you made folders for the course, even though I suggested doing that. So if I don't have, like, let's make a new folder and I'll show you what happens. So let's say we want to make a new folder really quickly on the desktop. We'll do it in quotation marks here, and we'll just call it like test folder with a bunch of spaces. Oh, sorry. We need to make directory here. So now we've made this folder on the desktop that's got these spaces in it, And if I try to change to that folder, which I can do I mistakenly already tried to do that. So on step 4, I can just write CD. Now, if I try to do this without quotation marks, it's going to throw up an invalid syntax error because computers, generally speaking, don't know that this is all meant to be one string. They assume that this space here means that I'm changing commands. So now what I want us to do is basically say, how do we fix this? And we fix this by enclosing it in quotation marks. So I do this here, and you can see now I'm able to navigate to this folder. Now, in general, you should still not put spaces in your folders. That's a really bad idea for the reasons I just showed, but one way to make sure that you don't make simple mistakes in that process is to just enclose your folder names in quotation marks always. Okay, so that's why we do that. The final thing I wanted to say about changing directories, this tilde here on on Mac systems basically means the current user. So if I actually go here and pull, by the way, I'm going to delete these folders now because I don't want them around. If I go pull, let's say the name of this folder, we'll just grab it from here. I hold down copy as path name. If I actually go ahead and put the name of the folder here, you can see it's users, Griffin, J, and Burr, then desktop code, SOC361fa24. Notice that this tilde here is understood by Mac operating systems to refer to users and then Griffin, J, and Burr. That's really nice. It's a cool shortcut where you don't have to write this out every time. However, if you're on Windows, I think there's a comparable Windows shortcut. I just don't know it. You may have to Google it. But if you're also uncomfortable with this notation here, you can always just go to the folder in question, click on it down here, or you could just go like right here, for instance. Let's go to the desktop right here. And I can just right click here and hold down the Option key on a Mac, and then I get copy as path name, and that's how I come here, and let's delete this and then just put it back with copy paste. Okay, so that's changing directories. Now, just a couple more steps before we get going. The versions. Stata has different versions, and we generally speaking need to put the version that we're using so that this code is forward and backward compatible with later versions. I personally prefer version 16 for certain commands, but just for the sake of simplicity, what we should do here is just look up our current version, which you can do from the command line. Here you can see this is version 17, so since I'm writing this code on version 17, I'm just going to remind myself that I did it this way. And version 17, when there are higher versions of Stata that come out, version 17 will switch the version downward to the lower version and make sure that your code still runs. Stata doesn't often make huge changes to code, like how commands work, but it has started doing that a little bit more recently, and you can have some annoying forward and backward compatibility problems, so make sure you change the version. Now finally we're going to log our data, or log our session actually, not just the data, in the folder that we're in. Now here, like I said before, you may want to put your log file specifically in the folder that you're using for the week if you do it this way. So if I wanted, for instance, to put this log file into this week 2 folder, since I'm already in this base folder here, what I'm going to do is just type a dot, and that says use the existing folder you're in, then a /, then the name of this folder. So I'll just write that, SOC361fa24 week 2. Oops, week 2. And then I double check it, and then I just write a /, and now I should get, if I run this command, a log file started in that subfolder. Okay, and we could see here there's already a mistake. This happens all the time. I don't clip mistakes because this is, just how the coding process works. So let's double check and see why this might not have gone how we wanted. So here we can come and see, okay, let's check this file path really quickly. So SOC361fa24 week 2. What I could do is just copy this, not copy as a path name, just copy it as a name. So if I come here, I could copy, and this should just print it as a path name. Oh, it didn't, but it shouldn't have printed as a path name, but that's fine. Let's just take the folder that we want and do this here. And then what we want to do is see, okay, am I actually in a folder that exists? And, oh, if we check it out, we see, hey, when I was demonstrating before that I was actually in a test folder, I could navigate to a test folder. I actually stayed in that test folder, and unfortunately that folder doesn't exist. So if I write print working directory, it says macOS refuses to provide that information because we actually deleted that folder. So we're going to change back to the current directory. So let's do that now. And now we should be able to log this. And okay, great. We're able to start a log file. Let's open here, and you can see there's a lot of stuff in this already, unfortunately. But if we take a look here, we see this log file. We can open the log file. Nothing super interesting so far, but you can see that we have some information here. We'll check it out at the end of the session. Okay, finally, we are ready to start actually pulling some data into Stata. So as you can see here, I said you should always write comments as necessary, and I mentioned a few different ways to write comments here. For the most part, I prefer the asterisk, which is the most similar to other computing software. So let's just delete this, and let's tag what we're about to do. So we're going to pull the GSS data and analyze it. Now, we're not actually going to immediately analyze it. We're going to practice pulling in data from different sources, but what we want to do is essentially make sure we feel good about that and then go ahead and do the analysis later. So let's pull the GSS data and analyze it. So now we want to tab back to our folder and see, okay, I put my information in the data folder, and here I see, okay, I've got GSS 2018. So I'm going to say, I can kind of just look at this path and see that I'm most of the way there already. I'm actually to this folder. So I can just navigate to the data subdirectory and then pull the actual data. So I'm going to write use and then quotation marks. By the way, delete this, of course. And I'm going to write a dot to invoke the current directory / data / GSS 2018. No need to append it with DTA. So let's do that now. And I can just run the whole thing again if I want, right? So I didn't need to run the entire do file again, but it's good practice to write your do file so that you can run the whole thing at once with no errors. In fact, that's the only acceptable practice. So now you can see here that I've got the GSS data pulled up. In the variables window, I've got a whole bunch of different variables. I can search for things like education. Here, you sometimes want to use stems, right? Because, for instance, the variable education is actually called educ, and it doesn't have in the label the word education. You can see here it doesn't actually have it, so be careful when you're looking for things. Don't put too long of a string in there. And then we can move on. So I'll show you a little trick in a moment. First of all, let's say we do something to these data. So let's do something like this. Let's say we have this education variable, it's in years, and what if I want to make an education variable that's in months? Of course, this is sort of silly because I'm just going to multiply by a constant. That's not actually necessarily the number of months that someone has been in school, but let's say for whatever reason I want that. So I'm going to say gen months educ equals educ times 12. And you can see I generate some missing values. Those happen whenever you have missing values in the original variable. But now what I want to do is try to pull in new data. We've pulled the GSS data, and now what I want to do is show you how to pull some other pieces of data. So, for example, we could pull the CPS data in. If we look at our SOC361fa24 folder, we come here, we see it's called CPS 2019 extract. Okay, so we can either, you can copy this as a full path name if you want. You could just copy it like this. Again, it turns out it looks like Mac is actually by default these days copying file paths as, or copying files as file paths. Let's see. Yeah, we actually get the full file path, which is really nice. But here, I'm going to clean this up a little bit and just call it in the same way as this here. So let's try it. So we'll write use.data / CPS 2019 extract. Let's give it a go. Uh-oh. No, data set in memory has changed since the last save. So Stata will actually prompt you to save these data because we did go ahead and make a months of education variable, or to stop the changes. Unfortunately, this message is very cryptic. It does not tell you how to fix the problem. So you would need to either, I guess you would just infer that you need to save. Now, as I mentioned on the syllabus, you generally should not actually save your data. The reason for that is this. You want, number one, to track all the changes you make to your data set. And number two, you want those changes to be recorded in a do file that is actually operable. But number three, if you have changed the data, then the cleaning that you do in the do file will no longer make sense. I'm not going to demonstrate that because that would take us a little far afield. But for instance, you could think about things like, let's actually just look at one small example. I'll show briefly. So let's say we write drop wealth, whatever that is, a question about whether or not the government should reduce income differences, right? So we do this. Now, let's say that we put into our do file that we wanted to drop wealth. So if I run this now, you can see this variable is not found. We actually have already deleted it. So this is not the exact same way you would get to this point, but my point is if I now save the data and I write down in my do file that I dropped wealth, now that command is inert. It does not actually do anything to the data, and in fact, it throws up an error. So the best thing to do is to say, don't make any changes to your data, like don't save the data, for example. What you want to do is instead just write down all those changes. So if I did want to drop wealth, what I would want to do is do a couple of things. First, I'm always going to append any use command I use with clear all. That pulls all the data out of memory. And then I'm going to load the data fresh as I got them from the GSS website or the NORC website. So this is the version of the GSS that's publicly available. By the way, the CPS 2019 extract is slightly modified, but all I did was drop some variables, so it's more or less what you can get publicly. Now what I'm going to do is try the same thing, and if I run the drop wealth command, you can see that it actually drops it because I've pulled the data fresh and wealth was actually in the data set. Notice that if I run the same thing again, I don't get an error message. I can rerun the do file from the top because I am pulling the data fresh with no modifications made, and in this fashion, I can write down what I want to do to change the data and also have that be a command that works that I can always retrace my steps. Extremely important data management pip. Okay, so practical takeaway, write clear all. And what that does is basically tell Stata, don't worry about saving because I'm going to delete everything. So we didn't actually want to use this command, so let's replace it with clear all. Now, we should be able to do this, and let's just run the whole thing again. In general, like I said before, your do file should always run in complete fashion. So you shouldn't have a do file where it's like, well, this command worked when I hadn't already run this previous command. It's a common, type of mistake. Your do file should be written so that it can be run in one go. Okay, so now I can pull the CPS data. Now we're going to go lightly over the next stuff. We're going to write clear all, and then, by the way, you can also append use with clear like this, but clear all is a little bit better because it clears everything from working memory, including some types of files or variables that may not be obvious to you. So clear all is a little bit better. And now let's use the Detroit area study, which I believe is just called DAS 1967. And whoops, that's 1976. Difference of 9 years. And this works here too. So that looks pretty good to me. And you can see here, this data set's a little bit messier, but it, just by leaving educ in the variable window, I see some information about the respondent's education. Okay, so cool. We've now done, if we come back to my set of exercises here, essentially this first task here, importing data. As I mentioned here, don't worry if it seems silly to clear, load, because now we're going to basically come back here, mark these sections off with comments. You can do whatever you want here. Working on the CPS data set is probably fine. Working on the DAS 1967, probably should tag these. So CPS 2019 data, GSS 2018 data. I'm a little anal retentive about this, but you can comment however you want. The comments are just there for your edification or that of your readers. Okay, so now we have these marked off, and we're going to do some specific data manipulation to each one. We can delete this now because we don't really need it. Okay, so what we want to do is go back to my exercises and see, this is, by the way, stuff we all talked about already, what I wanted you to do. By the way, I decided when I was changing different versions of this document, I decided that I wanted to start putting, instead of dollar signs, little inequality braces around the part of the data where, or part of the code where you should input your own things. The reason for that is that technically, as I mentioned before, a dollar sign in Stata actually has important meaning. It's just meaning that we shouldn't use. But I think there's a major risk of you accidentally doing things with that. All you need to do is run a do file once with the dollar sign in it, and you can get unexpected results. So I'm just going to write these types of things here. So notice that if you write sum and then your var here, like sum, this will do nothing. It's a mistake. Stata actually tries to process this as an inequality. It doesn't matter if I pop in v220, it still says invalid. So this will just throw up an error, which is better. Basically what this means, again, is in place of sum inequalities your var, you just want to write sum educ or something like that. So for instance, coming back here, let's say we wanted to get the GSS data up again. We could write sum educ like this, run it, and we want to adjust our window a little bit and then redo, and now you can read the results here. Okay, very cool. So here's what I want you to do. In the GSS data, and again, you may want to pause at various points, I wanted you to make a variable called retirement age that indicates whether someone is old enough to collect Social Security or not. There are many ways to do this. The fastest, I think, is to write gen and then, again, strip out these inequality signs, new var, and then you want to say equals, and then some condition. For example, gen in 20s, this is not the actual question, equals age greater than 19 and age less than 30, which is logically equivalent to someone being in their 20s. This is what's called Boolean assignment. So what it does is it basically is smart enough to tag people who fit the condition with a numeric 1 and everyone else with a 0. So it makes a dummy variable super quickly. So that's Boolean assignment. Now, let's go ahead and try that, but for retirement age. And I implicitly asked you all to do a little bit of research here. I want you to look up when someone should be retired in the United States, at least when are they legally entitled to collect Social Security. So let's do that now. Let's look up Social Security, United States, 2024 age. Typos are okay, not with the year. And we see age 62. Okay, now it looks like if we look at the Social Security Administration, this, by the way, is something you should always do, is take a look at these nuts and bolts. So let's actually just look at the PDF. If you wanted to only refer to retirees, you should do at least a little bit of gumshoe work like this. Let's see where it said about timing. I remember seeing the number 62, so let's head to where they said 62. Okay, so if you retired age 62, that's the earliest possible, your benefit will be lower, so maybe many people want to wait until 67. Now here, this is a little bit complicated. The full retirement age is 66. If you were born from 1943 to 1954, they don't actually directly tell us if you were born in 1957 or earlier when that was, like what the dates were. And they tell us that it increases gradually. So let's do this, since we might just want a general cutoff. Let's say 1967, since that'll cover a lot of our data set. Now, this is obviously sloppy. If you really cared about retirement age, that was integral to your project, you should look into it in more detail, but we're just going to take the easy way out. So we wanted to say gen retirement age equals, and here we only have one condition, which is that someone is 67 or older. You can write a greater than or equal to, but probably the simplest thing to do is to just say, since there aren't, if I look at age, there aren't non-integer values here. So there's no value between 66 and 67. I could just say, let's say that the person is older than 66, right? So we'll say gen retirement age equals age greater than 66, and we'll run it. Whoops, and sorry, actually accidentally ran the whole thing, so that worked, but then it cleared it. Let's run just this part, and now we have this retirement age variable. Now what we should do is check our work, and the way to do that is this. If you come back here to my file, I suggested that what you may want to do now is to write the command bysort, which basically says sort the data by some dummy variable, and then across levels of the dummy variable, some continuous variable with detail. So let's do that now. We can actually just copy paste this. Let's do this here. So dummy var is retirement age. Notice that you can abbreviate things in Stata, but it's generally good practice to write out the whole thing. Sum, for instance, is short for summarize. Abbreviating commands is fine. Abbreviating variables often gets you into trouble, so be careful. So now we'll write age, and let's run that. And this is pretty cool. You can see that when we have retirement age equal to 0, the largest values are 66. And when we have retirement age equal to 1, the largest values are 89. So that's really nice. Now, there's one little trick here, and unfortunately Stata does not make this clear to the reader at all. And it is this, if you come back to my notes. Technically speaking, people who are missing on values, on any variable, sorry, not values, but variables. If you're missing on a variable in Stata, technically speaking, missing values are written as dots or things like dot, dk, etc. And in Stata's way of representing things, this might seem kind of crazy, but it's true. They are represented internally as being arbitrarily large integers, which means they are not actually pure missing values. Other systems, like Python, for instance, use genuine missing values. However, unfortunately, Stata does not. It internally says these dots are integers, are just way bigger than everything in the data set. So what that means is that one way for our statement old var, here I wrote 4, I didn't really need to write 4, is equal to some condition to be false is for the old variable to be missing. So for example, when I come back to Stata and I look at my command, I say gen retirement age equals age greater than 66. Actually, one way, not for it to be false here, but for it to be true, is for age to be missing, because Stata internally represents that as being essentially equal to a very large number. So we want to come back here and write replace, this is how you fix that, retirement age equals dot, if you can just write missing age equals dot. And that'll cover all the ways something might be missing. So sometimes you see things that are written like dot .dk or dot .na like that, but missing covers all those cases. So now let's run that here, and let's actually just look at this command, and you can see this actually caught some mistakes we made before. It caught 7 people that were wrongly assigned to being of retirement age when really we just didn't observe their age at all. So that's an important point. Okay, cool. Now, if you really want to double check, this is not a bad idea, that missings on the old variable are really assigned to missings on the new variable, try putting in this user contributed command, which we access by writing SSC, which I think is for the social science something. It's almost like SSCC, confusingly, but it's actually totally different. I think it's a server. Server is one of the words. Anyways, it's basically a repository where lots of Stata code is posted, and when people write cool commands that are not official Stata, you can actually install them by just writing SSC install missings, and this is one of the most useful commands. So let's actually copy all this here, and we can now go ahead and write SSC install missings. If it's already installed, that won't do anything bad. You can see I already have it installed, so all it does is just say that they exist and they're up to date. If they're not up to date, it'll just update it. And now we can write by sort. Again, this tells Stata to sort the data by this retirement age variable, and then over levels of that variable, that's what the by part is, do a missing values report on our old variable, which is age. Let's run that now. And you can see here, this actually does exactly what we want. We see that people who had a retirement age of 0 or 1, there was no one who was missing on age. The only people who were missing on age were missing on retirement age. So that actually solves the problem we were concerned with before. Okay, cool. So let's move on. Now we want to make a value label and a variable label for your new variable. I realized that I left out the variable label syntax, so I'll show you now. But to make a value label, you basically apply this syntax. You come here, let's copy this, and then we'll take a look at it. By the way, you should comment on what all this stuff does. For instance, we do this in order to, let's write it like this, assign people who are missing on the old var to missing on the new var, etc. So you should make that type of comment. I'm not going to do that every time because it'd be a waste of time, but you should be doing that so you remember what all this does. So here we can go ahead and make a new value label. Now I want to tell you something important about how Stata works. Stata implicitly assumes at the end of these lines here, which actually in its internal representation, it knows, so to speak, that this is a different line than this, and it knows essentially that these commands should not be joined together. The downside of that is that if we have a command that would go on for a really long time and stretch way off into the distance past this white line essentially, then if we want to like move down some of this text here so that we can run one command over 2 lines, Stata doesn't do that unless we tell it explicitly to do that. So I'm actually going to show you how to do that. Let's first get rid of this comment. And now let's go ahead and write here 3 forward slashes. This is a line extender. And it's going to tell Stata to actually take the command here and then run it through the next line. And if we needed to run it across 3 lines, we could do this and write some more stuff here, but we don't need to here. And now let's make a value label. So value label is basically going to take our retirement age variable, which is now just a simple binary, Boolean, Bernoulli, dummy, indicator, whatever you want to call it, variable. And it's 0-1 coded, but we might want to remember how we actually coded the thing. So we're going to make a value label, which is a nifty feature of Stata that doesn't exist in a lot of other languages, where we essentially keep the numeric values underneath the hood, so to speak, but we can actually have Stata show us text or string values for the variable when it's displayed. So let's write label define, and you can call the label whatever you want because it's in a different namespace than Stata's variables. What that means, that's a little bit jargony, is that this could be called like retirement age. It doesn't matter that we already have a variable called retirement age because a variable and a value label are in different spaces internally. Here, though, I think it's generally best to just pick short labels. So let's just write RA. Again, we're not going to use it very often. Most of the time when you make a value label, you use it once. You define it. It's basically what other languages call a dictionary, which links numeric values and text or string values. And then our next step is going to be to label the values of our new variable with the label name. So this step is kind of like making a name tag, and this step is like putting it on. Okay, so here we don't even need necessarily the line extenders because we only have 2 values, blah, 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 but that's okay. So let's say we want zeros to be people who are working age. Now we want to be careful about that because, of course, there could be people in the data set who are not of working age and are not retired, like people who are 0 to 16. But here, if we summarize age quickly, yeah, we have the information here. We see that the minimum age in the data set is 18. So fair to call people working age. And then 1, we're going to say retirement age. Doesn't mean retired, but of retirement age. So we're going to define this label. And we can access that label by writing label list RA. And we see the label that we just made. Looks good. But now the point is going to be to label the values of retirement age, the variable, with this value label. So we're going to say retirement age here. We're going to apply the value label RA. Now, if we tab retirement age, Here, it's not a bad idea to do it. And actually, why don't we just rerun our command from here? This is kind of convenient. So we'll get a sense of how these labels work. If we look at retirement age, we can see, great. Now we have retirement age equal to working age, and then we get a summary of the age of the respondents here. Then retirement age equal to retirement age, we get a summary of the respondents on age here. And then finally, we have no observations, meaning they were only missing values when retirement age was missing, which is intended. Okay, cool. So that's more or less the first task. Now, I did say that you should try to label the variable. That's as simple as writing label variable, retirement age, and then some string value. I just didn't put it in the notes. So let's say something like this. Is the respondent of full American retirement age? And I see this is a little long, so I'm going to again extend this line. And then whenever I have a line extended, I often like to indent so that when I'm just looking at the code, I can see where, okay, this is actually two different lines that correspond to the same command. So now let's run the whole thing. And you can see if I pull up retirement age here, I should see the label. And now this label is nicely set up so that it looks like all the others, and I can remember exactly what this means. Although our name is pretty evocative, I think, so not a huge deal. All right, let's keep moving. So next, I asked that in the CPS extract, you make a variable indicating whether someone is married, called simply married. So since we're using a variable that is already, not all red, but already categorical, we do need to get under the hood a little bit because, as I mentioned before, Stata actually has numeric values for these categorical variables underneath the hood, and you can technically make a new variable by accessing the value label for the old variable, but it's faster and less headache-ish to just access the numeric values. You'll see what I mean in a moment. So let's copy this here that I suggested doing, and then we'll see how that works. So let's go to the CPS data. Again, notice I'm not saving the data. I'm saving my do file. I have not saved these data at all. I should not do it because all the changes that I wanted to make are recorded here. Notice that I can rerun this however many times I want and it still works. So I've now made reproducible research. You should not save your data in general unless you need to do a lot of data cleaning. You wrote down all the changes in a do file and you still have access somewhere to the original data so that you can always show how you got the modified cleans data set. Now, sometimes that's useful to do from a workflow perspective, but for the sake of our course, you won't be doing a lot of data cleaning and you need to get into a good habit from the start of writing down all the changes you make in a do file, not saving the data. Okay, so we can clear this all out, right? I can clear it out. Oh no, I lost all the data. All my work is gone. No, it's not. I can pull it up again and we're good, right? Same exact thing. We've got retirement age here. Okay, so no need to save as long as you write down how you change your data. So let's come to the CPS data. Clear all, let me write that again. Use CPS 2019 extract. Let's run that. And now we have the 2019 CPS or current population survey data up. And let's look at the variables. Because this is a huge data set, like if we summarize all the variables, you can see the smallest number of observations we have is 89,000 people. The largest on marital status is nearly 300,000. So huge data set. So I only kept a few variables to minimize the size. Pardon me. Still feeling a little bit under the weather. So now, let's see what I wanted us to do exactly. I said that we should make a variable indicating whether or not someone is married. So I think our best guess is going to be to look at this marital status variable, predictably enough. So here, just to inspect it, I can pull it up in the command window. This sort of thing where, I want to look at the variable initially, but once I know that, I probably don't need it in the do file. You can just do it in the command window. Okay, so I see that people were married, widowed, divorced, separated, or never married. So what I want to do is take this variable and based on the value of this variable, assign someone to a binary variable indicating that they were either married or anything else. So I could do that in a couple of different ways, but the simplest is going to be, well, the most foolproof is going to be to do this. Let's write describe old var here that was called marstat. And I see that this information tells me the value label for marstat. So I want to go see what numbers are associated with these value labels so that I can say if someone was, I'm guessing this is a 1, but I don't know, make them married on my new marital variable. And if someone was a 2, 3, 4, or 5, make them unmarried. I don't know that that's true out of the gate. I would guess that that's true, but that's why we're going to look at the value label. So we go pull the value label. You can just copy paste. And let's write label list old var value label, which is what we just got. We can delete a couple of extraneous spaces. And what do you know? We guessed correctly, or I looked at the data before I did this. So here is our value label for the variable marstat. And we've got married, widowed, divorced, separated, never married, corresponding to the numbers 1 through 5. Well, integers 1 through 5. So now what I want to do is write gen new var. Here, let's just say, I think I said to call it married. Yep. Let's write gen married. And then here, notice that this is the same sort of syntax as before with gen retirement age, except here I had an inequality. I wanted people to be retirement age if they were older than 67. But here I want an equality because I just want to assign people to married if they were 1s on the old variable. So here I don't even have 2 conditions, I just have 1, so I can delete all this stuff. And old var here is the marital status, and the numeric value, or numval1, is just 1. This again is a Boolean assignment. By the way, I'm going to delete these comments here. You should replace them with comments that actually make sense to you. So, by the way, remember to save your do file, even though you don't save your data. Now, if you look at this type of assignment, you can see this is the same sort of thing. This syntax might seem a little bit weird, though, at first, if you really look at it. I write gen married equals marstat double equals 1. What does that mean? What this does, and we can enclose this in parentheses just to emphasize it, even though it doesn't matter. We can interpret this as saying, make a new variable called married that, since it's equal to this condition, it's just going to tag people as 1 if they fit the condition and 0 otherwise. And it's going to essentially say, let's evaluate whether or not marstat for a given individual is equal to 1. Now, there's 2 kinds of equal signs in programming, and this is universal in programming. And this is actually a fun mathematical point. Sometimes we write equal signs in math, and we say things like, pi is approximately equal to 3.141592, etc. Now, that's true by definition because Archimedes' constant, which is the number pi, or the numeric value of pi, could be given any letter, right? It doesn't need to be given pi. It's presumably given pi because it's the constant of the perimeter, essentially. But it doesn't necessarily need to be associated with that symbol. It can just be derived by doing, inscribing a hexagon inside of a circle and inscribing the circle and the hexagon inside of a square. Fun proof. Anyways, when we define pi to be equal to, like the Greek letter pi to be equal to 3.141592, etc., what that means is that we are just defining it to be true. And really what we should do is use exact notation that mathematicians actually do use and write something like colon equals or a triple equal sign, which I can't write easily here. So that's what mathematicians do. When they say we're setting something to be equal by definition, let's do this. In computer science or computing, the way we write that is we just write a single equal sign. Notice that we've already done that in a couple of different places here. So when you write a single equal sign in computer science, you are assigning. You are not, is there another instance? No, just the 2. You are not actually evaluating. The double equal sign behaves like an equal sign when we have like essentially a lookup function. So in a way, if we say something like 3x equals 5, something like that, okay, of course, x is 5/3, but if we have an equation like that, let's actually do something a little more complicated. Let's say 3x plus 2 equals 5, something like that. If I work a little bit of algebra, and my next step is, just doing this off the top of my head, 3x equals 3, That second equal sign actually is kind of interesting because that's no longer an assignment. The first equal sign was an assignment. It basically defined 3x plus 2 to be equal to 5, just arbitrarily. But the second equal sign is actually kind of just saying, by the rules of algebra, we know that this is not true by definition, but it happens to be true because we manipulated the equation according to legitimate logical rules. So that kind of equal sign behaves a little bit differently, and a way that we can sort of use the equal sign differently to say, evaluate whether something is true or not, is to use a double equal sign. So if we want to evaluate whether something is true or not, and I'm realizing my analogy is a little bit inexact, but maybe that gives you some of a sense, right? The second equal sign in that algebra equation I gave is kind of basically saying this could be true or false. It's not true by definition, but it happens to be true because we got there by valid inference. So this is essentially similar in that it's saying marstat could be 1 or it could be something else. If it's 1, assign people to 1 on the new variable married. If it's 2, 3, 4, or 5, assign people to the value 0 on married. So let's write gen married equals marstat double equal to 1. This is a common mistake, by the way. We can see what happens if I don't do the double equal sign. Let's start with that. And you can see this is an invalid name. Stata doesn't like it. Unfortunately, the error message is not very informative, so let's try again. And hey, here we go. Okay, so now, next step is to check our work. So let's come back to the exercises. Now, the way we check our work when we are going from a categorical to a dummy variable is to, instead of use a table of means, like tab sum or bisort sum, those both work well when you have a new categorical variable and an old continuous variable. But here, that's going to produce a problem because our old variable is categorical as well. So what we want to do is do a two-way table or a crosstab. And for each row of our new dummy variable, we should get a matrix that has only one column that has non-zero entries. And the basic logic is that we want to send everyone who fits a certain category to only one status on the new variable. So let's check our work here. So we're going to write tab married marstat, and now conveniently we can just include the option missing to make sure we cover missing values. And okay, it looks like here that we didn't actually have a ton of missing values on this variable, which sort of makes sense because it was the variable that had the most observations. So maybe everyone had that. We can actually double check by writing missings report marstat, and we don't have any missing values, so that's good. If we had missing values, of course, we would want to go back and say replace, we can actually just do it, married equals dot if missing marstat. Notice that this won't do anything wrong, it just doesn't make a difference. So the syntax is the same as before. So here, let's actually spread this out a little bit, and let's actually flip the order. So let's go tab marstat. We can actually just come here. Let's write tab marstat married. Oftentimes, transposing a matrix, swapping the rows and the columns makes it easier to read. So here, okay, this is a lot better. And we can now see, you know, compared to this here, when we do it like this, I guess my rule from before, by the way, I should have said, as long as you have the old variable and then the new variable, you should only have one non-zero entry across each row. And then here, in this case, you should only have one non-zero entry for each column, basically. So here it's rows. And we can see that if someone was married, they were assigned to a 1 on married. And if they were widowed, divorced, separated, or never married, they were assigned to 0, which makes sense. So now what we want to do is make a new value label for our dummy. I didn't show how to do that directly because we did it up here. So let's actually just copy our syntax here and write label define. We can just call this mar with 2 R's, let's say. 0, unmarried in any way. Maybe we just put that there to remind ourselves that even if someone was widowed, that's technically not married. And then 1 will be married. Okay. We can define our label, and now we can paste it on. So we'll write label values, in this case, marital mar, like that. oh, and we see our variable, actually, sorry, I forgot what I called it. It should be married. Case in point, you often have these type of little typos. So let's do this now. And let's label our variable. So label var, and we'll write married, and we'll just write whether a respondent was married at time of interview. And now we can just tabulate our beautiful new variable, tab, married, and let's write something interesting. Let's check wages, right? So we can write tab married sum wage 1. Let's see how this looks. And you can see that people who were unmarried generally earned significantly lower wages than those who were married. We could do a t-test, for example, by saying t-test wage 1 by married and unequal. Here is the correct option to use. And you can see that we, of course, have extremely strong evidence of a statistically significant difference. We have a t-score of a massive 62, which is much higher than whatever the correct critical t would be. Since we have such a large number of observations, it'd presumably be right around 1.96. Okay, so we can do some basic analysis. Now, let's go ahead and in this same data set, check for some implausible values of hours worked last week. So this is a little bit of data cleaning. And actually, I realize now that as a matter of fact, in this version of the CPS, hours worked last week is not in there. So this is something of a common occurrence. I realize that maybe someone, in this case me, uploaded a newer version of the data. So let's go back to the course GitHub. We can actually more easily pull it up by just going to the syllabus and here, and let's go to week 2. And now what I'm going to do is actually re-download these data here and replace them in the folder that we're using. So I'm going to do this here. I'm already in the data folder, and it's going to ask me if I want to save over it. I do, because I want the updated data. So I'm just going to replace, and then now I can rerun this whole thing here, and it should have the updated data, and indeed it does. So we've got hours last week and then another wage variable. Okay, cool. So let's take a look at this variable hours last week. And let's look for some implausible values of hours worked last week. So why don't we go ahead and write sum hours last week, D for detail. And we see, okay, so some people worked allegedly only 1 hour last week. That kind of makes sense if someone is mostly retired, puts in a couple consulting hours. Of course, even the first percentile, people worked at least 4, so these people were outliers by some definitions. See, the median person worked 40, the average person worked 39, essentially, so that makes complete sense. But I noticed that people at the 99th percentile worked 80. That's an awful lot, right? If there are only 5 days in a work week, you can quickly infer that that's 16 hours a day. If they spread it out over all 7, that's still quite a lot of work, right? That's approximately 11.4 or something like that. 11 and 4 sevenths, not 0.4. But quite a large number of hours. So we might say, okay, that's getting a little bit suspicious. Now, are there any values that are totally implausible? And I might think that from a physiological standpoint, at most, brutal industrial revolution conditions, someone's probably working 12 hours a day, maybe 6 days a week, at most 7. That's got to be the maximum, right? And a little bit of quick mental math tells us that 12 and 7 together, multiplied, are going to be, 14, carry the 1, 8, 84. We can double check our math, by the way, by writing display and then 12 times 7 here. So display, unfortunately, you always need to write that in Stata to do basic math, and then you just write an asterisk. And we see, okay, we did our math correctly. Great. So that means that these people who worked 168, now I might think, geez, how many hours are there even in a week, right? And if I say, okay, I want to do 24 times 7, so I do 20 times 7, okay, 140, plus 4 times 7, okay, 28, so that's 168. So some people said they worked more hours in a week. By the way, let's check our work. That's 24 times 7 here. So 168, some people said they worked every hour. 3 people said, remarkably, this is a well-cleaned data set, but even still, some people skirted through who said they worked more hours than there even are in a week. So that can't be right. So then, according to my exercises here, what I wanted you to do was drop people. Of course, we could just tag them, but probably for this purpose, we want to drop them because we know those people were very mixed up about some aspect of reality. We want to drop them from the data. Not necessarily permanently again, but we want to drop them temporarily. So when we load this data set and then work with it, we probably want to drop those people. And then we may want to rerun some of our analyses to see maybe some of those people also reported crazy wages and this test will change. So let's go ahead and do that now. We'll say drop if hours last week. Now, what do we want to do here? I'm going to say that if we come back to the data, it kind of feels like, you know, maybe 80 is the absolute maximum someone could realistically be working. That still feels like a huge amount. I may want to, you know, you could use the 2-key rule for outliers, right? So you could, I'll show how to do that in a little bit, actually. Let's put that off. But that's just a algorithmic procedure. It's not scientific. So I might say, you know, I'm probably just going to use my gut and say 60, maybe 70 feels like the most someone could be working. But again, even 60, that's 12 hours a day for a 5-day work week. And then, you know, for 7 days a week or 6 days a week, let's say 6, right? That's 10 hours a day. For 7, that's nearly 9. So it's getting to be pretty large on a day-to-day basis. So we might say, okay, I think I'm probably just going to cut it at 60. So let's say we drop if hours last week is greater than 60. That's how we would do it. Now that deletes a lot of people, but notice that this also deletes people who had missing hours of work last week, because remember that a missing value is counted as an arbitrarily large number. Now we may or may not want to do that. It depends on the context. Here we might say if someone didn't report their hours last week, their information might be compromised. If we only wanted to drop people who were larger than 60 and not missing, we could simply add the condition and not like this, missing hours last week. And we could run this here. Well, let's actually rerun the whole thing. And now we drop substantially fewer numbers of people. Now we just dropped the superhumans, the Stakhanovites, who were working more than 60 hours a week. That was only 5,300 some people, or 5 1/3 of 1,000. In a data set of, geez, you know, at least close to 100,000 people for some conjunctions of variables, a couple 100,000 for each individually or marginally. That's not that big of a deal. Okay, so that's how we could do that. Now let's finally come back to the last exercise. Use the Detroit area study data set. I want you to make a value label for the marital variable. And the point of this is not actually so much coding, but it's actually basically to just learn how some older data sets are a little bit funky in how they code missing values. So let's pull up the DAS 1967 data. And you can see here we've got a bunch of variables that have, first of all, kind of annoying names. One thing that I didn't mention but is important to know is that Stata is case sensitive. So if you don't want to have all of these guys, like if I try to sum, let's say, what do we got here? Racial composition of the block, probably. Let's look at that one. So I can write sum v12. Okay, first of all, I have no idea what these numbers mean. There's no value label. Second, if I try to write sum v12 like this, I say variable not found because it's case sensitive. So one thing I may want to do is rename everything to be lowercase. So to do that, I just write rename asterisk, comma, lower, like this. And now everything is lowercase, which is good. Now, what I wanted to do was to look at the marital variable. I could do that in a couple of different ways. What I recommend doing is looking at the codebook and use Control F to try to find the marital variable. So let's write merit, something like that. And I see that that was variable number 24, and it's the respondent's, present marital status. So I'm going to go find V24, presumably. Now, there's a couple of different ways to do this. First of all, I may want to make sure that these numbers actually do correspond to the variables in the data set. So if I look here, I see it looks like these are just numbered 1 through, in this case, whatever that number was, 24. So, okay, I'm probably fine if I look at that. I should see 5 different possible values, and then 9, 1 is NA. So let's come here and let's tab V24. Okay, and I can see I've got 41, 574, 35, 30, 99, and 1. If I come back here, 47, 792, 42, 35, 121, and 1. So these don't match exactly. That might be cause for concern. That could just be a feature of the data set. If I look at the value label, I do see that it looks like this says respondent's marital status. If I come here and I write MAR, there's only one variable that comes up. So that might be something to look into later to make sure that the codebook and the dataset don't disagree for a big deal reason. But I can punt on that. So then what I asked you all to do in the exercise was to make a value label based on the codebook. So I'm actually just going to copy paste this and put it into my do file. It's not the correct format, but I can see that it's kind of close. So I can write something like label define. Here I can call it MAR again because I've switched data sets. So I can write like this. And then now just note that I need to match the format. So 1, we can say single. 2 is married. So this is a little tedious, but we just do all this. 3 is divorced. Let's do that here. And I might write an extender now because this is kind of long. And I'm going to say 4 separated or a spouse absent for other reasons. I'm just going to say a spouse absent for whatever reason. Probably not important to have that in the actual data set. 5 widower. Let's just say widowed. A little more conventional. And then finally, 1 person was coded NA. Now, this is really problematic because in lots of older data sets, you will see missing values actually just assigned to numbers like -1 or 10 or 99 or 1,000. And those can be really confusing because, I said before that in some contexts, Stata understands missing values to be infinitely large. However, it does not always do that. And in particular, it can run most commands while knowing, again, quote unquote, that you don't want to include missing values. So if you write summarize or tab or whatever, Stata is smart enough to omit missing values. It's only with some of these logical comparisons that Stata gets a little bit tripped up and accidentally counts the missing values as arbitrarily large. So here we have a problem. This 9, we should really try to get to be a missing value, right? And we need to take a couple of steps there. Here, what I'm going to recommend is actually that we don't bother with this label. So let's just delete this. Let's label our variable. And then let's remember that at the end, we want to replace, let's call this variable married as well. Sorry, let's just use the original syntax rather. So replace v24 equals dot if v24 equals 9, because that was the value that was problematic. So we wrote our value label. Now let's paste on the label. So label values v24 mar, and then let's tab v24 miss. You can write missing out to see how this works. Okay, cool. So now this looks pretty good. We have v24. All we did was label the variable so that now we remember what all those numbers mean. Of course, they're still underneath the surface. We could write tab v24 no label, and we see that they're still there. But in this case, first of all, it omitted the missing value. Second, it stripped away the value labels. And we see here, this looks pretty good. We have single, married, divorced, separated, spouse, absent, widowed, and a dot. So we've done some basic, really useful data cleaning. of the sort that you'll need to do all the time if you are working with any but the most pristine data sets in Stata. So that's more or less the basics. I obviously could go over very many more techniques, but at this point, I think you have a good sense for how you do some of these basic things. I'm going to show you a couple of other advanced techniques in a moment, but I'll take a quick pause here. So I'm back. Let's go ahead now and look at some of the advanced techniques, which are already arguably useful to you, but especially as you proceed further, this way of working will become important in order to save you time and will also allow you to do all kinds of interesting analyses that require some customization or require doing things that maybe a particular technique doesn't have a standard command or something like that. All kinds of reasons to learn some of these advanced techniques. And what I really want to show you here, more or less, is just loops. Loops are very much like a sum. So a loop in computer science basically means that you tell the program to, for a given set of values, execute some kind of operation and do that until you reach the end of the values, which you might remember sounds a lot like a sum. And so loops have a really intimate connection to discrete mathematics and the techniques you learn in that type of class or setting. And you all already know a little bit of discrete mathematics thanks to our work. So loops are often a really good way to do something in Stata where you know that you want to repeat some process a few different times, but you want to maybe change it a little bit each time. So I'll come back to an example of that in just a moment, but let's show that, for example, we could actually calculate the mean and the variance of some of our variables by using a loop. So I'm going to introduce a couple of techniques here. First, I'm going to introduce you to the command local. Even though this does not look like a command, it is one. And what the command local does is it stores information in a temporary variable in Stata, which disappears after a given run of a do file. Or if you're working interactively, it persists until the end of a session, meaning you close the window. So this part you'll need to run all in one go from your do file. And locals are basically a way that you just make very temporary variables. They're not columns of the data set, and they're things where you can reuse the name after you run a do file a particular time, etc. In most standard kind of mainstream computer software, programming software I should say, this is just what's called a variable. Now, to access the contents of a local, you have to do this in kind of a funny way in Stata. You do that by using the left and right tick marks that you see below. So for example, we define a local variable called sample total. We set it equal to 0 here, but then later we, in the middle of a loop, redefine sample total as being equal to its own value plus the value of miles per gallon that we're on from a loop between 1 and n, which was here defined to be 74. So you can kind of probably already work out that this is essentially just summation notation. It's telling Stata to sum over the values between 1 and n, we already defined n to be 74, and add them all to the sample total. Now, the reason that I say local sample total equals in tick mark sample total plus miles per gallon is that I want to have a cumulative sum. So I want to say at each stage, take the existing total and then chuck on this other value. MPG with brackets in it, and then a number just accesses the jth element of the column MPG. So I did this with the auto data set. Why don't we open that data set, by the way? So let's come here and we'll write sysuse auto. And we can put that in our do file if we want. Let's actually clear all. And we can actually just say, like, let's look at MPG2 like this. Display. And you can see that's 17. Now, if we open the data set with the command browse and just look at it like a spreadsheet, we can see that the second element of the MPG vector is the number 17. So that's pretty cool. We can actually just immediately invoke those values. So what our loop is basically doing is saying go from values j equal 1 down to 74. And at each stage, take a value, add it to the sample total, and then redefine the sample total to be the existing total plus the next value, plus the next value, plus the next value. And that's what this loop is going to do here. By the way, the command, or really the sort of prefix for values here, tells Stata to iterate over integers. You also sometimes want to iterate over things like variables, in which case we'll write the syntax for each, to be discussed in a moment. In other software, these are both just called for loops, not, they're not for values or for each. That's okay. Stata is just a little picky about the syntax, but essentially these are, if you know a little bit about programming, these are for loops. Okay, so let's go ahead and try this here. And then you can also notice that I do the variance as well. So I write local sum of squares equals 0. Then for values j equal 1 to n. Notice again that I use the two different tick marks, the left and the right tick mark, to invoke the value of a variable. And then I say, okay, in the sum of squares local variable, take the existing sum of squares, so it starts at 0, but then it quickly moves on from 0, and then add to it miles per gallon for the jth observation, minus here y bar, and I'm going to define y bar as the result of our sample total over n, so that's just the mean, square it, and then I'll look at the total sum of squares divided by n minus 1. That should be the variance. So let's copy this. And we'll need to get that irritating page number out of there. So that's here. We'll get it out. So let's take a look at this. Let's just run this part here. First we'll, this is MPG, right? So let's just write sum MPG. And let's notice that the mean is 21.29, etc. Now let's say we run this part of the loop here, and we see that our loop correctly calculated the sample mean. Now let's see if we can get the variance. So we need to run the whole thing again, because again, now if I try to write display sample total, it's not going to give anything back because that variable was only defined for that run of the do file. So let's now pull up the sum of squares. So we'll run the whole thing. And now you can see that the sum of squares divided by n minus 1, which is the formula for the variance, was 33.47. And here the variance was 33.47. And they're actually exactly the same, rounded. So that's a loop. A loop essentially is like a sum. But we often want to use loops for things that are not basic sums. Of course, you shouldn't actually find means and variances this way. This is just demonstrating that they're basically the same thing. But of course, you should just let Stata calculate that for you. But now let's do something cool with a loop. So for this specific problem, what I suggest that you do is make a set of dummy variables that indicate that that should actually be an observation, not a variable. Common mistake. I made it myself. That an observation is an outlier on various continuous variables in the CPS and standardize each variable. So let's actually do that now. And I actually gave you the syntax directly here because this is a little bit tricky. By the way, let me note one thing here. The braces are necessary for a loop. In other programs, you also need to use braces or you need to use spacing. And the indentation here is also necessary. So this is one click of the tab key. Okay, so here we have this for each variable, or a for each loop. And this is going to basically iterate over each var of var list, var1, var2, etc. We're going to plug those in. And then it'll do all these operations. So it will sum the variable quietly. Quietly means don't display the results, which is often helpful when you have a loop. And then we're going to assign to the local variable q3. These are what are called return values. Return values are the results of a command. So for example, if I do something like summarize MPG, I can access the mean by writing display rmean. I can access the standard deviation by writing rsd. You can always get the values that are available as return values by writing help, name of the command, here summarize, and then going to the very bottom, and you can see these stored results are given here. So in this case, if we plug this in here, basically, I'm going to adjust, by the way, this in here. I'm going to say for each var. Now, var here is the name of the index variable, essentially. So before we had j, which is a little more standard, but here I'm just going to write var because that reminds me of what I'm doing. And I wrote var list, var1, var2, var3, etc. Here, we're just going to put down the variables that I suggested, which were hours last week, age, and wage 1. And you don't need the commas. We've got this here. We do need to pull in the CPS data, so let's do that here. And we can write, let's tag these. So loops, they are basically sums, or similar to sums. Can't type, sorry. And let's say standardizing variables, and standardizing and tagging outliers with loops. So we can pull up our CPS data. And okay, we need to change our working directory. So it looks like at some point, I think I double clicked something and I got to the wrong directory. This is a pretty common problem. So if I print the working directory, okay, I'm in week 2 here. So I need to actually back out. A way you can do that is to write change directory and then the trick I mentioned before, double dots, to get booted back to the higher level working directory. So now I'm in the base directory and this should work, and it works this time, good deal. So what I want to do now is run the code here, but I want to explain what's going on. So what this says is for each, again, it could be for in another language, variable of this variable list, and you do need to include variable list here. You could also make a local that has all of these in it, but that's probably too complicated for our level. You can do a lot of loops just using this explicit syntax. I'm going to have the loop quietly sum the variable, put into Q3 and Q1, these local variables, rp75. You can see from the sum help file that in the stored results, rp75 is the 75th percentile, rp25 is the 25th percentile. So I could just use these directly, but I want to put them in helpful names. And then I'm going to put y bar as the name of the mean, and s as the name of the standard deviation. I'm then going to define the IQR as Q3 minus Q1. And then I'm going to, for each variable that I have in this list, make a new variable called outlier underscore variable. So it's going to make a name that's like outlier hours last week, outlier age, outlier wage 1. And I'm going to set that equal to, again, Boolean assignment, 1 if the variable is got a value that's greater than Q3 plus 1.5 times the IQR, or it's less than the variable minus Q1 minus 1.5 times the IQR. Okay, so by the way, this single pipe character is computer science for or. In Stata for and, you can just use the ampersand. While I'm at it, I'm also going to make standardized versions of the variable, so I'm going to write z underscore variable, and then I'm going to write the variable minus its mean divided by its standard deviation. So let's run all that now. And you can see now in my variable list, I have outlier variables on outliers or on hours last week, on age, and on wage. And then I've got standardized variables, z for hours, z for age, and z for wage. We can summarize some of those variables. So one handy trick is if you have a bunch of variables that all share some kind of prefix, you can write something like sum z star, and that'll only sum variables that begin with z. Here, I think only those standardized variables start with z, so that's easy enough. And you can see, okay, I've got z hours last week, z age, z wage. They all have means that, this might look a little bit weird, but hopefully you know that in scientific notation, that just means they're extremely small numbers. They're not exactly equal to 0, but they're very close to 0. That's just because of rounding error. If they're off from 0 by like only, whatever 10 to the 11th is as an actual name of a number, you're probably good. They each have a standard deviation of 1, which is what we would expect. And now what we could do is also look at some of these outliers. So how many outliers on each variable? We could just come here and write sum outlier asterisk. And you can see, okay, so technically on hours last week, 61% of people were outliers. No one was an outlier on on age, but then many people were outliers on wage. So what that means is, first of all, the two key rule is a little bit of a blunt instrument. We may want to inspect some of the data by hand. So let's say we write, let's say tabulate outlier. We'll just do this here. Tab outlier wage 1, and then sum wage 1. And then here I can see, okay, so these people who were outliers, basically they had a mean of $49 an hour if they were people who fit the criterion of being outliers. And in this case, they were earning a mean of $16 or $17 an hour if they were not outliers. Okay, so this is kind of interesting, and I realized that I actually overlooked something here. So this is a good self-correction. It looks like many people are outliers on wage 1 and hours last week, but when we actually tabulate outliers on wage 1 and summarize, these values look really reasonable. We don't actually have many people who are outliers on this variable. Only here, actually, roughly something like, 1 in 18 or something like that. So not too bad, but this is a little bit mysterious. Why do we have such a high mean for the outliers variable? Well, it turns out that I forgot to put into the code that we need to replace outlier on the variable equal to missing if we are missing on that variable. So this is the same sort of thing as before. It's a very pernicious mistake. You can see that I just made it now. And if we do all that, and then, summarize. Oh, we need to make a little thing here. I think we have a typo. Yeah, typo here. If we run all that now, you can see that this looks much more meaningful. So we have these outliers here. We still have 32% of people on hours last week, probably because we had so many people with crazy high hours. But now the outliers on wage 1 are much more meaningful. And if we go ahead and tab outlier wage 1 and sum wage 1, notice that these numbers don't change because those people are missing on wage 1. So we don't actually directly observe them. Stata is smart enough to know that. But on the actual variable itself, the problem is that when it's just directly counting people, it would not realize that missing values are missing truly. They're not just infinitely large numbers. So that's a very common gotcha. Again, even I make that mistake. So I will fix that part of the code and upload that. But that's basically where I think you can end. Now you know some basic and advanced data cleaning techniques in Stata, and in the next part of the video, I'll talk about accessing data from the ICPSR. Okay, hi everyone. So in this part, I want to talk a little bit about how to find data on the ICPSR, or Inter-University Consortium for Political and Social Research, sometimes called IPSR. So let's first take a look at the homework for which you're going to do these things. So the homework is under the assignments, assignment 2. And if we take a look at it, we'll see that you are instructed to do the course exercises for chapters 1, 2, 3, and 4. So let's pull up Gordon's book. I think I can just pull this up here like this. And we want to look for course exercises 1, 2, 3, and 4. So course exercise. And we've got to do a little bit of scrolling here, but that's okay. So course exercise 1, write 3 research questions in your area of interest. Okay, not too bad. We don't need the data for that. Let's keep progressing though. So course exercise 2, use the IPSR to locate possible data sets for each of your hypotheses or research questions, scan the documentation, yada, yada, yada. You might need to do, take a close look at this. I won't walk through this in tedious detail. I'll just show you generally how to do it. Choose one of the data sets. This is the part that actually the first sort of part of this lecture goes over. Choose one of the data sets and then actually go ahead and access the documentation. As I showed you before, you could do that with the Detroit area study. Locate the list of variables, questionnaires, and skip maps, and so on. Basically what this means is actually go ahead and take a look at the data and try to understand what the researchers actually did. So what were the actual questions that they asked? Are there any tricks or gimmicks that you need to be aware of, etc.? Again, we've kind of gone over that briefly, not in a ton of detail, but you saw how I did that for the Detroit area study. And then finally, here, course exercise 4, download the raw data, create an analysis data set, independent and dependent variable, recode the variables as needed, etc., and show some, basic kind of data processing that you might want to do. Okay, cool. So now let's take a look at the IPSR. So let's go to, I'll open a new instance of Firefox here actually, and I'll show in a private window so that you can see what this looks like when you're not logged in, how you want to log in. Of course, I have the website saved to my favorites, but I'm just going to Google it. So ICPSR, you can just Google. You go to the Michigan website, and you can see here that there is a lot of information on this page. In general, you can, the best practice with most websites like this, big data repositories or any other kind of website that sort of seems to attempt to bowl you over with information at first, almost always using the internal search function right here is going to be more useful than trying to navigate in the way that they suggest. So I would just go ahead and get started searching. By the way, some websites don't even have very good internal search functions. So a little tip you can use is to go here to the URL bar and then write site and then the URL that you want to use, just url.com for example, and then to put in quotation marks your keyword that you want to search for. That's a really nice way to search using Google and a website internally, even if their own actual internal search function is not very good. So just a kind of tip there. Now, we do want to log into IPSR because we'll occasionally need to, not all data sets can be downloaded without an account, and it's best to have an account even though it seems kind of pointless or irritating to need one. Not very good for reproducibility in the long run, but this is how it's done. Okay, so you can access it through your institution. You can also sign in with email. Note that there's no sign up function here, but basically if you don't have an account, this will get you an account. So I would just click access through your institution, type in Wisconsin-Madison. Okay, that doesn't work. So let's try Madison. Okay, and then you can see we could click on this. A little bit slow, so just give it a second. Select here, and you'll need to log in through Duo. Now I already have an account with IPSR, so I'm not going to do that here, but this is where you could go ahead and get logged in, and you'll need to just do an email confirmation, that sort of thing. Okay, that part is kind of self-explanatory. So let's go on to the IPSR website, and I will log in with my own account here. And now what we're going to do is start searching. So let's say that I am interested in something like, let's say, maybe mental and physical health and markers of stress. So let's say I'm going to look for biomarker stress data. So when I search a keyword like that, you can see that I get a fair number of results, even though I put in some quite specific terms. Now, you'll sometimes search for things, for instance, if you just search for something like income, you're going to get an enormous number of results. So one thing to be aware of is that even to narrow down the field to just, about 750 results, you need to be pretty specific. So here you can see the search results are sorted by study relevance, which is not always the best algorithm. It's not actually totally clear. One thing you can do is do most cited, which is kind of interesting. So here, National Longitudinal Study of Adolescent to Adult Health, AdHealth. This looks pretty good. I've heard of this. I've heard of Kathleen Harris. So maybe I'm thinking, okay, this sounds like maybe what I want to look at. But I also see some other information here too. Okay, Midas, I've heard of that. Maybe that sounds good. So you may want to just search by most cited rather than use their internal study relevance. You could also do sort by time period or when it was released or updated. So here you can see by time period. Unfortunately, we don't actually get the listing for these two. We can see this is 2018, 2017, And then we might go to the very end just to see, okay, so here we've got like Costa Rican longevity, 2005. So we're getting older. We're also getting a little more specific. Maybe you're interested in Costa Rica, maybe you're not. So you'll need to do, just a little bit of filtering of the results in different ways. Some of the other things, you can also expand the summaries, although that's generally not that helpful. And you can kind of look around, look at variables, for instance. Here, now this is not typically that useful, but you can try to sort just by variables that you might be interested in. So here I might look for something like, let's say heart disease, nothing. Okay, blood pressure, nothing. Okay, so maybe it's not that useful depending on the context. So let's suppose that we are interested in this Midas thing, because I might say, well, I've heard of that. That's something in my field I'm interested in. So now, maybe what I'll do is, rather than flip through this, why don't I just search for Midas? So that's a pretty unique name. Okay, 36 results, that's a lot. But now maybe I can say I'm interested in, let's say I'm interested in the period right before COVID, since COVID really makes a lot of data gathered during COVID are especially unreliable, and we have to be very careful about that. So let's say I'm going to look at, 20, daily diary project. There's a lot of different things here. So we may want to look for just something kind of general. We've got the Midas refresher here. Maybe now what I want to do is just click on one of these things and see. Refresher, by the way, usually refers to an additional part of a sample that's done in order to basically, if you have a certain amount of study attrition among certain groups, you need to get in more groups. So here, this looks like this might be sort of the baseline or the original study. We've got some other things here too. I'll click a couple of these and then plan to take a look at them. You can see we've got these really specific samples. A lot of times, this looks like the original project. These are quite old data, but it might still be useful to go back to the original source and then take a look at it. I can see here a lot of people from Wisconsin. You might actually have seen some of these people in our very building, interestingly enough. So we are looking at these data, and I might go ahead now and just read the summary so that I get a sense for those more updated data. Where did those come from? What are those based on? So here I'm going to read a little bit. See, the midlife in the United States is a collaborative, yada yada. This is pretty boring. This is the interesting stuff. Collected survey data from 7,000 people, roughly, 4 subsamples. Okay, non-institutionalized English-speaking adults in the coterminous United States. That basically means the lower 48, which is often a restriction. Sorry to Alaskans and Hawaiians. 25 to 74, okay. 30-minute phone interview, self-administered questionnaire, so on and so forth. Okay, we have these 3 primary data sets. And we can see here we've got the twin screener data. That's something, just skipping ahead to see the simple things. Coded text responses. Okay, basically they took some open-ended text responses and then gave them categorical codes. That might be worth looking at. Let's look at the main thing though. So we've got siblings and twin data. And we can see here this contains responses from the main survey. Respondents were asked to provide extensive information on physical and mental health. Blah, blah, blah. Okay, so this sort of sounds like what we're looking for. So now we have a sense for what the original data set did. We might take a look. Okay, this is just called Midas 2, and this is just called Midas 1. So maybe this looks like something that we might be, this might be what we're looking for, essentially, if all they did was reproduce the data, but did it a little bit more recently. You can still see here lots of people from Wisconsin affiliated, which is nice. You might actually be able to go ask people in person if you want. Most people are happy to talk about their research. So here you can see, looks like they did a follow-up on the original Midas samples. Guiding hypotheses, blah, blah, blah. They added an African-American sample from Milwaukee, Wisconsin, so right down the road. And it looks like this might be kind of cool. Might be what we're looking for. So let's now go back and let's see if we can actually find like a third version of the project And this is kind of the process you have to follow. Do a little bit of investigative work, see if you can work backwards, reverse engineer certain things. We might want to now look at the refresher because maybe they didn't redo. Okay, well here's I guess -3. So probably this is. Let's actually look at the refresher first and see what this did. So replenish the original -1 baseline cohort. Okay, split into 2 data sets, blah, blah, blah. All right, so that sounds kind of like an update. Let's look at this data set here. And we see role of behavioral, psychological, and social factors. Okay, this is a third wave of the survey on longitudinal participants. Okay, so basically what it sounds like is this looks like it's a follow-up from 2011 to, or that's right, 2013 to 2014 of the original participants. So these are panel data, and it looks like they just didn't merge the data sets, which is fine. And this here looks like it is a new version of the study. So it might be interesting to just start fresh here. This recruits 2,100 new participants, and let's see here. We can get a little bit more information. Okay, interesting. So yeah, we'll want to take a close look at this if this is our project, but I might go ahead just to get started a little bit and download the data. You can see here you've got a lot of different formats. More than likely, you're going to want to use Stata. Now, you might have some old data sets where you don't have Stata data available. I'll show what to do in a moment, but here we're going to download these. So I'm going to put it in my data folder. Now, I may want to start a separate folder for this project, but for the sake of keeping things manageable, you can just use the format we've already used. But in the long run, it's probably good to organize projects by folders. And there's kind of a question here of whether or not I should use this name or not. I think I'm going to not, even though it is nice in some ways to maintain the names of folders as we find them online. Here, I have a suspicion that I'm not going to be able to remember this, so I might just write Midas refresher 1. And I'm not going to tag this with a date because I'm not making this file, and it doesn't really matter that much when I personally downloaded it, as long as I tag the dates, tag with dates, files I make that pertain to this. Okay, so that's a zip file. For those of you who don't know what that is a way to compress information, which is actually a pretty interesting topic in its own right, but not one we have time to talk about at all. But basically what happens is you compress information so that it can be transmitted without taking up a ton of space. You can see this is already a fairly large file, even though it's been compressed or zipped at 46 megabytes. But we are going to uncompress it to access it. Typically, you can just double click on this, but I like to make sure I know how my computer is going to open it. So I'm going to come to open with and open with the archive utility, which is just a folder or a tool program that unzips zipped files. And now I'm going to come move this compressed file to the trash because I don't need it. And now I'm going to rename this folder again so I remember what it is. So we're going to write Midas refresher 1. And now I'm going to open this. And holy moly, there is a lot of information in here. So this is typical of how actual research works. There's very often more information than you can shake a stick at. So I might just start looking through some of these things. So I look at this here. Okay, this looks like we got the DDI codebook. Not really clear what that is right out of the gate. So I might just flip around here. Sorry for seeming sort of informal, but this is how you would actually do this project, right? You wouldn't know these things in advance. So I just picked a data set I've heard of but haven't used so that you have a sense of how this works. By the way, just incidentally, how do you hear of data sets in the first place? Or how would you, say, come up with a data set that you want to access that might be on IPSR, but you don't need to search for it? just read papers that are interesting to you and find out what data sets they use. I think, that's how most people in practice actually find data sets. It's sort of a word of mouth thing rather than people just kind of searching. Okay, so anyways, we see here, this is documentation of age. And, okay, this describes procedures for obtaining information about MIDAS refresher respondent age. Okay, that's pretty specific. I may want to now just take a look at this. The README file is often a good place to start. So this seems like it's a good guide to all the information that we might want. For instance, it refers to that age document we saw. We see the weight information, which I discussed last week. We don't actually have time to cover that. For the most part in this class, constructed scales, the variable crosswalk, so that what that generally means is ways to harmonize variables across different waves, coded text, other important information. So I would probably start here, mark this thing up, and then start reading it. But typically, you can look at the questionnaire. These are often useful. This tells you how the questions were actually asked to the participants. You can see here that we have some cases, as I mentioned before, where non-response in some way is coded as an 8 or a 9. Sometimes the data set that you actually get will already have that problem fixed, but other times it won't. We'll just need to see. There's a whole bunch of other stuff here too. There's another zipped file. I'm not really clear what this is, so I'm not going to open it right away. Usually the data sets are in these DS folders, so let's see here. Okay, we've got this codebook here for the aggregate data. There's another file or folder here. This is the coded text data. I think I'll wait on this and I'll instead look first at the data here. Now you can see this supplemental syntax. I'm going to open this. Oftentimes these files actually do the cleaning for you to some extent. So it looks like this actually will do all that cleaning for you, which is really nice. So you don't actually need to, what this is doing basically is taking all those kind of silly ways of coding missing data. So as a -1, 8, or a 9, as I mentioned before, those are pretty conventional. And it's actually sending them to missing. Of course, this is a giant do file spanning some 2,600 lines. So you may want to actually just not do this and then go ahead and do it on your own, frankly. So let's actually just open the data set. And here, I'm going to cheat a little bit and just double click on this to get it into memory, even though what you should actually do is set up a do file where you load this in. So this looks okay to me, looks kind of interesting. There's a bunch of recession experiences here. Let's take a look at some of these things. Diagnosis heart attack. So let's just say we're going to tabulate that here. And some people have had a heart attack, others haven't. Looks like about 1% of our sample had, but many people responded inapplicable. So we may want to see, it says diagnosis heart attack. So maybe I misinterpreted that. Maybe it doesn't just mean that they had a heart attack. Let's go back to the documentation and check that out. So let's look at one of the questionnaires. We've got the SAQ again, which is this sort of thing here. Why don't we open both of these files actually? And let's look up heart attack. Okay, I don't see much in the SAQ, so it's probably in the bit here. And let's double check that we know the name. So we could actually probably just search for this. Oh, and it's not in there, which will sometimes happen. So let's try to go to this area. Okay. So it looks like that variable is this base plus a here. Okay. So it looks like there was a suite of questions that basically only applied to people who perhaps had heart trouble. So it might be the case, this is one of those skip logics where people only were asked A, B, C, etc. if they said yes here. So we may actually want to go back and just look at this base variable here and see if people have ever had heart trouble. So we come here, and we may just want to take a look at this. Okay, so about 14% of our sample has had diagnosis of heart trouble before. Okay, interesting. So what we could do is then say among our total sample, which is about 3,000 people, presumably everyone who has had a heart attack has been told that they have heart trouble. So then we could come here and say something like this. Again, we'll just get this number. Okay, 55 out of, it looks like these inapplicable people are people that just haven't had heart trouble. So it seems fair to say actually that about 1.5% of the sample has had a heart attack, but we wanted to just take a look at that carefully. Now, of course, we could also just search the data set and see, did they ever directly ask participants this? So here, if we actually just directly look at the ever had a heart attack question, it looks like we got more or less the same results. So if I were really interested in heart attacks, I might want to just search here. You can see there's an enormous number of questions here, so got to be careful. I might want to go back here and search for heart attack and see if I can find this. Okay, maybe it's actually in this. Nope. All right, so if I wanted to find more information out of this heart attack variable, now what I might do is go back here, RA1PA8, and see if I can find this guy. Okay, there's a bunch of things here. Let's try to go to previous. All right, so come down here. For some reason that didn't show up in the search, but that's okay. We can see it looks like they more or less just straight out asked people this question. And it looks like this applied to everyone. So anyways, we're kind of getting off into the weeds here, but the idea is that now I have a sense for how the data look, why some questions might be a little bit unusual, like why did most people not answer this question? Well, it was a skip logic question that people only answered if they had previously said yes to some other question that was meant to screen them. So now, how would I do this in a systematic and rigorous way? How should you submit this for your homework? You want to open a do file. So let's just say we do it like this. We'll come back to our folder. We're going to open, in this case, what did I call this? Lab 2 homework. Oh, sorry, this is actually the homework file for the last homework. Let's come here and pull up my do file. So yeah, the one I made before. So this was my data set that I made for the exercises for this week, or my do file. But what I'm going to do now is actually just copy the stuff I like and want to use again for the homework. And let's say I'm going to save this as 2024-09-17. So it's 361 fall 24 homework 2, like this. And I'm going to say practice, cleaning data and Stata. And now I just want to start saving these things in a systematic way. So I'm going to now write out how I would actually access these data in a systematic way. So I see that I have to go into this Midas refresher folder. So I'm going to write use, I'm already in the correct working directory, so I'll write data, Midas, no need to worry about case, by the way, with file names. That's actually not something where case matters. So I call this Midas refresher 1. And then I'm going to keep the folder structure, even though it's a little annoying. DS0001, DS0001, and then I'll just copy this here. I'm not changing this, and in fact, I could just copy this as a path name if I want, so I think I'll do that. And this is fairly lengthy, so I'll just remember that I'm already in this folder because of this, so I can just replace all of that with a dot. Still kind of lengthy, but this should work. And okay, indeed it did. I'm going to keep these names here so that this is maximally reproducible. All I did was change the name of the actual, kind of root directory here to Midas refresher 1. But then everything else I left as is, so that all I need to do in the future is just get this data set again and rename only one folder. Okay. So now what I could do is go ahead and start, let's say I was really interested in those heart attack data, and we found that heart attack here. let's see, this was the variable of interest. So I might go ahead and start doing some of my tools from before. So let's say I'm going to investigate heart attack data. First of all, I'm going to rename everything to lower. And then I might say this should actually now be lowercase, so RA1 PA8. And we'll run this whole thing. Okay, and looks like I miswrote that somehow. PO, I swapped those. Okay, so again, common mistake you'll make. Okay, and now I've renamed it, so I need to remember that I need to write clear, of course, common mistake. I might as well tag this now. Okay, so we're learning. Okay, we've got ever had a heart attack here. Now I need to remember that this variable, I haven't actually cleaned the missing values, so what I want to do now is describe the variable and go ahead, okay, look at the value label, so that's just called this here, so label list, you can just write lab list, this, and okay, it looks like don't know refuse, inapplicable were 7, 8, and 9. So again, I could use that giant cleaning do file that I saw before, but it might be nice to just know how it's being cleaned up. So I can do that on my own. So let's say replace RA1 PA8 equals dot if RA1 PA8 equals actually here it looks like we could just write greater than what, 6, and that should be fine because that'll take values that are 7, 8, and 9, or values that are maybe possibly already tagged as missing, because again, those are represented as infinitely large internally. So this should be fine. And okay, it looks like that was 62 real changes. Now I probably want to rerun this command. Come up here. Okay, and we just have people down to yes and no, and I could also just tab RA1, PA8, miss. Whoops, I keep writing that wrong. Sorry, guys. And okay, now we can actually see the missing values here. So that looks good. So if I come back to the Gordon exercise here, it sounds like what I was meant to do was to download the raw data, create an analysis data set that contains at least 3 variables, the case ID, a dependent variable, and an independent variable. So maybe I want to say that the heart attack is the dependent variable, and I want to find an independent variable. So maybe I have something here like age. Now there's a ton of age information, so let's say I want to look at RA1 Prage here. Let's see what that looks like. So again, we'll play around in the command window. Okay, this looks good to me. So let's take that, and also let's see if there appear to be any missing values. There don't right now. Presumably 23 through 76, that information is all valid. Why don't we take a look, though, at the code book, as we often should. So I think this is just called Prage, partially. Okay, so it's not in the phone interview. It's not in here either. So now we might want to just search for age. Unfortunately, sometimes these code books are a little bit, they don't work exactly the way you would hope. All right, so I'm just going to tediously search for age, more or less. And it looks like we might be here a while. Perhaps we'll need to do a little bit more digging. And this might be information that we need to even look in yet another. Well, now I'm remembering we have this age questionnaire. Actually, maybe we should open that. So documentation of age. So let's come here. Here's the procedure. Okay, we're looking at this here. They were asked for their birth date, and then basically they were, they just simply took the phone interview date and subtracted the birth date from that, and it looks like this is how they found this information. So, yeah, some people reported. There's some interesting stuff here. You want to take a look at this. But it looks like there aren't a ton of outliers or things like that. Okay, so this is kind of interesting. It's left up to the individual analyst whether or not to include the age outliers And it looks like for the most part, this is actually not a variable on which we have missings or anything too weird. Okay, so let's say I want to keep these two. I also need to find the case identifier, by the way. So here, that's just this MRID. Now, you probably also want to keep some of these other variables in a more serious project. You want to keep the weights, for example. Those are also kind of IDs in a sense. They're important things that need to be included in every analysis. But I would say for this purpose, you can just include the ID. So let's double check that this looks like it should. Okay, it's a giant variable with many possible values here, which makes sense, right? Because it should be uniformly distributed because there should only be a unique ID for each person. So that looks like what we want. So let's say we're going to keep that and age. And we can actually just come here and write keep RA1P8, all these things here. We'll run this whole thing. And now we just have a small analytic data set that includes their age, heart attack information, and their ID. And then we can do some basic analysis. For example, we may now want to bracket up the data. A couple of different ways to do that. One way to do it is to just say, I want to put people into 5-year age buckets. You can actually do that in Stata in a couple of different ways. You could write, for instance, help egen. Egen is short for extensions to generate, and it basically helps you make new variables really quickly in Stata. So we saw how to make an age bracket before, just doing it by hand. But you might also notice that you've got things like cut, for instance, which allow you to group data pretty effortlessly. So you can use this group extension here. So this tells you the number of equal frequency grouping intervals, and you can basically put people into equal size buckets automatically, which is really nice. There's also this group variable here. So there's a bunch of different ways to do this. I think there's even some more you might be able to find. Now, you don't necessarily need to use that approach. You could just do it by hand. That might be actually the easiest way to do it. Whoops. At a beginner level. So we might just say, okay, let's find the full range of age. We'll actually summarize it. It's called this. And we'll come over here. We have minimum 23, maximum 76. Okay, so maybe what I want to do is just put people into big, broad categories. So let's say gen age bracket equals, let's say, well, we could do this in a couple of different ways. How do we want to do it? Maybe what we want to do is put people into, say, a bucket from 20 to, let's say, 40. That's around the age when people start having some more serious heart concerns. And then maybe we do 40 to 50, 50 to 60, and so on. Just something simple like that. So let's say we'll write gen age bracket equals 1 if RA1 per age here is less than, let's say we do 20 through 39 inclusive, let's say. So it's less than 40. So we'll make those people ones. Maybe best to make them zeros, but it doesn't really matter. And then now this is going to essentially send everyone else here. If we look at age bracket, so we could, let's just say browse. This sends a lot of people to missing. So now what we want to do is go ahead and replace those people. So replace age bracket equals, let's say 2, if RA1 per age is, we'll need to put a parenthesis around this, is, okay, so we want to include those people who are 40, so greater than 39, and let's say our age variable here is less than 50. So we'll include the 50, etc. So let's do that now. Okay, looks good. Now we could kind of just copy paste and just change a few things. So let's say greater than here. So we included 40 through 49. Let's do 50 through 59. So greater than 49 and less than 60. And we can run all this at once in a moment. And then for greater than 59. And then here we want the 60s. So we'll say less than 70. It's a little tedious, but you can learn how to speed this up later on, and we'll say less than 69, greater than 69, sorry, then less than 80. So let's run all this all at once. And now let's take a look at our age bracket variable. So let's say we tab age bracket, and then we're going to sum RA1 per age, like this. And okay, this looks pretty good. What I might want to do now is actually just go ahead and run by sort age bracket sum age d, and it's RA1. You could rename these variables if you want, like this. And now I can kind of flip through these things here, make sure I've done this correctly. So it looks like we had people who were 20 through 39 here, 40 through 49, 50 through 59, 60 through, in this case, 75. Oh, okay, we made some kind of a small mistake here. I didn't change this to 5. That's my bad. So let's try the same thing, run it all again. Okay, 70 through 76, 60 through 69, 50 through 59, 40 through 49, 20 through 40, or 39. Okay, so that's how you might, just do a little bit of double checking your data, making sure everything looked correct. So at this point, I would say you're more or less done with that part. Again, you want to double check the course exercise and follow all of the things that Professor Gordon says to do in that course exercise, but this just suggests one way that you might go ahead and start doing some of these things. Yeah, so I think I'll probably cut it off here. Feel free to come into my office hours and talk to me about the project if you want, and I'm happy to help you out, but that's how you would get started with the project by doing this part of the homework. And then you would of course want to save and all of that stuff, and your project might look a little bit different, etc. I guess, by the way, one thing we probably want to do is just tab age bracket and then look at that heart attack information as a bit of preliminary analysis. I sort of left that out. So let's look here, and you can see, interestingly, the share of people who've ever had a heart attack goes up linearly, or not linearly, goes up monotonically, I mean to say, as the age bracket increases, which is, of course, to be expected. And actually, it doesn't quite go up monotonically because the share actually falls from 4 to 5. So this is actually kind of an interesting fact. Some of these older people have actually had fewer heart attacks than some of these younger people, but that could be because people have gotten secularly more unhealthy over time. By the way, the last thing I didn't mention that you'd want to do is you'd also want to make a value label here. So I won't go through that in too much detail since I already showed how to do that before, but you basically do it like this: label, define, age bracket, like this, and then you'd say 1. We said here, we should probably say 23 to 39. Technically, we were saying we wanted to include people who were 20, but there's no one in the data set that small. 2 here, we'd say, these are 40 to 49, etc. This should probably be 2 here. And then we'd go on, and I'm just going to show how this works for a couple. Then we'd say label values, age bracket, because we called them the same thing. And then now we can take a look at the age bracket variable, and you can see some of these have been labeled. I just didn't tediously go through all of them, but you could go ahead and repeat the procedure as needed. And yeah, that's more or less how you would do this. So feel free to ask me if you have any questions. Thanks for watching.